So I'm going to talk about the Cinderella survey left to the end. Viking has turned up quite a lot during this talk and this conference, and save the best till last. So I'm going to talk about Viking survey, and I owe a lot to, in reverse order, Will Sutherland, who started the Viking survey application, built the camera and the telescope, and was instrumental in actually getting Vista to work, along with Jim Emerson. So Will is owed a great deal in terms of the legacy that Vista has. Good, I'm glad you're listening. And also, I owe thanks for when I took over the Viking survey to Conrad, Simon Driver, Steve Eales, and Richard McMahon in help in getting it over the line and through. And in particular, I will mention Angus as many times as I can in this talk, and his work on actually getting the data through. So Viking is in the Middle Kingdom. It's that Goldilocks, not too deep, not too wide, not shallow, and is importantly deep enough to see the rare objects, wide enough to see enough of them in a volume that they're interesting to select. In particular, it's the rare, very rich clusters of galaxies and the very rare, distant, bright quasars above a redshift of 7. It's that parameter space which we really was going for within Viking, where you need the infrared imaging. Can't do this with optical. You have to have the infrared imaging in order to do the selection. The wide, full hemisphere surveys just don't go deep enough to see enough objects. So it's that compromise between depth and area, giving you a certain volume, which is the important thing. And that's why the suggestion was to do the order of 1,500 square degrees at the Viking depth, and complement it with the VST kids area to give it the optical bands to allow you to determine whether an object you detect in the near infrared is actually red and not just blue. So in the end, the Viking survey is 1,350 square degrees. I'll get to why. And it, in terms of its science priorities, is about what you detect in the near infrared and what those properties are, not in terms of kids, which is the optical and the very high quality imaging you get in terms of weak lensing and the influence of the galaxy you can see in the optical on the background ones. Sky coverage, we've seen this plot a lot. Just to emphasize, the Viking area is on the equatorial northern galactic area and the southern galactic pole at -30 in the south galactic pole region. Relative depths and optical wavelength, just to give you an idea of the VST Atlas and VHS, full, almost, certainly hemisphere and almost hemisphere, the interesting bit for hemispheres for VST. So you're at AB magnitude of this. Viking goes down magnitude and a half. Euclid goes significantly deeper with video, but over narrower areas, and kids matches to much deeper in AB. But the interesting thing is, we are wanting to look at red objects, so actually making a detection here and not making a detection in the optical is the vital thing. So this quite large jump in optical depth to infrared is exactly what you want from an infrared centered selection. You don't want to necessarily go to this uniform AB depth. And to point out that this is an old plot. I didn't manage to remake them before I put this talk together. We did have a second round follow-up of Viking to try and push the depth in J a little bit more to get more distant quasars, but instead Sharks was chosen to go deeper in K, and Helmut described that, and that is going to have an awful lot of additional science gains in terms of the most distant objects. In terms of area and depth, so the hemisphere surveys are up here, so flipped a bit. So hemisphere surveys at the tens of thousands of square degrees. And depth here, Viking comes in, and again, Viking plus is out, but I'd put sharks in here. So quite irritatingly, I managed to get the colors all mixed up here. I'm red-green colorblind. The K band is the green, and the J band is the red stars. I don't quite know why I did that, but just to show you the relative depth in terms of the narrower, deeper surveys, sharks, DXS, and video of the order of tens to hundreds of square degrees, and Ultra Vista is somewhere down here. So the status is we have 1350 square degrees because we we were given a certain amount of time, clock time, and the overheads that were anticipated when we originally put the proposal in was that the readout would be a certain amount of time, and it was effectively double. When you add lots of small amounts of time up, it actually has an impact on the area that we were able to cover. It's fine. In orders of magnitude, this is nothing. And it was complemented with the VST coverage, so everything matches. There isn't very much of the VST where we haven't got Viking coverage and vice versa. And the shortfall is down to those overheads. And in any, it was one strip in declination, so the area, the volume, area on the sky isn't particularly ragged. It's all relatively straightforward to draw. So it wasn't a huge loss in area in the end. The final release is out and can be accessed in relation to the kids' data. Angus described that. And it's his very long-running and epic analysis that allows this combination of the kids and Viking data to go through. And it is important that ability to be able to deal with all 9 bands simultaneously and in the same system that allows us to do the sort of selections. Oop, ran through this too quickly. So this was something that Angus showed the kids 4 bands, U, G, R, and I, in terms of their A-B depths, and the 5 Viking bands. You can see there's a good uniformity in the peaks of these, and the schedule, the requested depths are the ones we reached without too much of a tail to the poorer end. And in terms of image quality, there is a little bit of a tail above seeing of 1, but the majority of it is well below and peaking about 0.8. And it all matches quite well with all of the U, G, and I bands, and the R band being the prime weak lensing band for kids. And in terms of depth, that's across each field. The field-to-field variation is relatively small over the whole survey area, and the seeing hasn't got any great variations at particular places. Angus was explaining that in the depth, there are occasionally fields where there is a diffuse nearby galaxy, and that increases the variance. So some of these variations are actually real physical things and not noise and systematics in the data. So that's Z, Y, J, H, and K, all very similar, low-grade patterns on the sky. The uniformity of the actual data quality is amazing. It's also designed to be a much broader survey. There are many more complementing surveys, as well as the VST kids. The gamma and 2DF lens, AAT omega, AA omega surveys, which sort of predated VST kids, but that area had been well defined. and there's a large amount of spectroscopy in those areas at relatively low redshift, and it is going to be the same area for the foremost waves survey. HST Atlas picked areas out of the gamma survey for deeper Herschel observations, as Helmut explained, and that gives you access to the more distant universe and the objects that are strongest in the far infrared. The Wallopy ASCAP prototype, the SKA prototype ASCAP is doing an H1 survey, and again is targeting the gamma fields and the kids Viking footprint. And Hyper Supreme Cam has almost completely covered bits of the equatorial strip, although slightly out in deck, but there's a very large fraction of Hyper Supreme Cam data in the kids Viking area. So if you build it, they will come. In terms of an equatorial field, it's important, I'll make a point a little bit later, that there is, for any night on the VLT, a part of the kids Viking area that is above an air mass, below an air mass of 1.3, all the night, for every night. So if you want to pick a target from a field which is relatively uniform, you can do it whenever, which is important. I have to get, put Viking kids into an image survey, this thing pops up, and it's, yeah. I'm not encouraging to give children axes, but it does make a good revision of an old adage about bringing up children. So in terms of this science exploitation, we have gone ahead and attempted to do the things that we said we were going to do, in particular the distant quasars and multi-wavelength IDs. It's now all possible. So the data is available through the DR5, or will be very soon. Line-bound photometry is there. The 9-band photometry currently is set on making a detection in the R-band, and talking to Angus and Conrad this week, it's pretty obvious that we actually need to just make an additional selection of going from the K-band and say all of the bands blueward of that, what are their relative fluxes? So we're actually not requiring that every red object has an R-band detection, which is currently what the release is, which makes a lot of sense from a kid's perspective, but from a Viking perspective, we need to look at, we made a detection in K, what are the other waveband detections, particularly if you're interested in the most distant or dusty objects. So we are principally concentrating on the infrared selection, predominantly the detections there, and not looking to sit at an optical faint detection and trying to work out its infrared properties. So first primary one was looking for the redshift 6 and above quasars, and it is well suited to that, but it is a very large haystack and a very few needles. And Brown Venemans, throughout the period in which the Viking data was taken, was working very hard to take data as it was collected to find the candidates, and did a very good job at finding most of the brightest ones. And if you were, at least until the launch of JWST, looking at the 10 most distant quasars, it's a hit parade which is not necessarily updated every week, but it is one which people take care to look at. Most of the top 10 for a lot of the last few years included objects which were found through Viking area. So it is that depth and that is the maximum potential of Viking. And just in terms of the color selection, in having the infrared bands in order to rule out other objects, particularly low mass stars, was the important selection. So Z, Y, and J, the combination of those bluer bands, were how you most efficiently detect the most distant quasars up here in this box that are blue in Y minus J, So they have a relatively flat flux from the Y to J band, but are very red in Z to Y. So there's a large break due to the Lyman alpha absorption. So they're red in one band, but blue in the other, whereas the low mass stars are red in both. And the galaxies at moderate redshift sit at the bluer end in Z minus Y. And in terms of the number that you're expecting per square degree, and importantly, you're looking at about 1 per 1,000 square degrees at this sort of magnitude, number counts, getting down to J of 21, you need at least 1,000 square degrees in order to find one object. So we are able with Viking to get into this regime where you might be getting tens if you're lucky and you selected them correctly. So that in terms of the depth that we can reach in J, which is why we were hoping to try and get into this regime by going a little bit deeper in the Viking area with what I referred to as Viking Plus, but that we didn't make a convincing enough case. And you know, other things will come along. Euclid will definitely do this very much better. So the depth of Viking is great to look at the distant universe, but it also gives you a lot of signal to noise in a red band, potentially looking at the more evolved stellar population of any local galaxy to look for color differences between optical and near-infrared surface brightness. So you can look at the morphology in the near-infrared, compare it to the optical, look at the disk, look at the bulge, and look at the relative population, particularly if there are large color variations. Star formation histories of the two should be very different. You should see that in bulge disk decompositions, and that was done 10 years ago from a gamma selected survey set of objects, and Sarah, who's giving the next talk, is going to go through more of that, so I defer to Sarah, who's been doing more of the recent work. But in terms of the gamma survey, which was predominantly a near redshift below 0.2 selection in terms of the spectroscopy, you've got a very good sampling of the local galaxy population. So being able to look at not only the most massive stellar population, but also the lower mass stellar population in the same volume and environment, looking at the differences in the stellar population, bulge and disk has been very important. And gamma and the low redshift regime, where H1 surveys are best and the radio frequency interference is less critical, we're going to be able to get a good census of the local H1 interstellar medium of galaxies. You want to have as wide a complement of well-studied, well-parameterized galaxies in the local universe. And waves will follow on from this and get you a larger volume when that survey starts next year. Herschel Atlas did a subset of the Viking kids area, the order of 400 square degrees, and there you're selecting the most distant dusty objects where the K-band is important to make your detections. And those are provided the identifications at the depth of Viking, and that's been improved with sharks by about a magnitude and a half, and a helmet described that. Smaller area, but the volume that you're looking at is still very significant in the distant universe. So if they'd done 1,500 square degrees or 300, we still have the same magnitude of problem of actually trying to follow up all of them. So give us 300 and we'll get on with it. So one of the other things I'm particularly interested in is the passive galaxies, which are predominantly in clusters of galaxies. And those are relatively easy to select from the Viking kids selection because of relative depth in optical and near infrared. You can pick up either passive or dusty or both. So you're making your primary selection in the near infrared is very possible when you have the complementary deep optical imaging and can determine some things are red. Not actually rocket science. It's so obvious, sometimes people need to say it out loud. Low mass stars equally are important, relatively rare population for the Y and T dwarfs. One thing that the Vikings kids area covers is a relatively wide range of galactic latitude. So just looking at the stellar population in the immediate region in going up through the disk in terms of the lowest massed objects, which are not going to be that far away, allows us to sample quite a wide range. So although they might not be very numerous, we can at least look at their relative population with galactic latitude and in terms of dynamics. So no survey stops, and there's always something else coming along afterwards. So HyperSupremeCam has done a very good job at filling in at least some of the deeper imaging and allow, particularly in the Z and Y, allow us to go a bit deeper. So it is crucially the K-band in anything where Euclid is not covering that is our greatest legacy from the VIKING Vista surveys. So we're going to be able to improve on the Viking depth in the sort of 1 micron region. And LSST will again push that even further and get us to the order of AB of 26, 27 in certainly the UGRI, maybe not quite Z or Y, but at least give us a complement, which is very good to actually get the reddest objects for Viking where we have a detection. We still have the detections. It's actually the ensuring that we have a matching optical very faint object to determine exactly what the relative color is that's going to be the important thing. We've got the near infrared at the depth at which we're actually going to be able to do spectroscopy with moons, but actually establishing in the optical the depth to require you making a joint detection is the big step that we need to make still. So just to emphasize that, this is the magnitude and wavelength plot again. So we are going in with, where are we? DES and down to HSC. We are dropping in AB in the Z and Y quite significantly, but that allows us to find the red objects that drop out, which we weren't able to when our limit was only here. Video is down here, and Euclid over a much wider area of sky of the order of 10 square degrees, of the order of 5,000 square degrees, is going to be critical. And again, sharks comes in at allowing us to look at objects which are even fainter in K, and subsequently the same relative color optical to near infrared we're going to be able to select in from HSC. So that's the imaging future in terms of Euclid. It's got the depth and an area that is going to supersede the 1,500 square degrees that Kids Viking will do, but there's an awful lot still to do in that. Spectroscopy is going to be the next step. I did have to make an adaptation from the previous version of this talk I gave 4 years ago, where all of this was a bit hand-wavy and things didn't exist. Well, things are very close to actually getting to telescopes now. So foremost moons and PFS are all, if we believe the predictions and actually bits of kit are sitting there ready to be shipped, within about a year, year and a half, we are going to be discussing spectra from all three of these facilities at actually being able to unlock the nature of the more distant objects. And moons in particular, given its sensitivity and given the relatively bright nature in Y and J and H for the most passive galaxies of redshift of 1, which we select with great ease from Viking, we're going to be able to get spectra of passive massive galaxies in a regime which is not possible with current instrumentation, unless you do one by one with X-shooter, which I don't recommend. So the legacy of Viking, as I mentioned, is that it will provide a set of objects, which if you wanted to do them one by one with VLT, which I've just dissed, but you're going to be able to do it with any instrument, and particularly with it in the ELT era, we're going to have to look at individual objects at any time of year and potentially require them to be relatively high in the sky. The Viking kids area is going to be a resource where we don't necessarily want to look at things from the whole sky, because that's just too much. But in the areas in which we have those very key resources of multi-wavelengths, like H-Atlas and Wallaby and the WAVES survey, we're going to be able to do a lot more. So one way to gauge the impact, and I looked at this 4 years ago, and there were 70 citations. There have been 3 times that many citations in the last 4 years for the Messenger article about Viking, and people have been picking up on using Viking kids data. Most of those citations are from kids Viking related projects, Gamma, H-Atlas, and whatever, but many of them are using Viking data to select quasars independently, and many of them are more general projects making comparisons. So there's quite a wide range of things which are using the Viking kids data. So it is that combination of the optical near infrared which is going to be important in terms of area and depth for looking at that particular region of universe of redshift of 1 to a few that Viking is going to be particularly good at. And the common objects, redshift 1, relatively passive galaxies, red quasars, which are difficult to select in optical surveys, M-stars, whatever, you're going to cover in large numbers. The rarer objects, distant quasars, low mass stars, and the more massive high redshift clusters, we have enough area to get reasonably good statistical samples. So we're now having an impact already in terms of the selection of objects, and you saw from Angus's talk and others that this data is having already a clear indication that it's having the impact that we said it would, and in terms of its use for future foremost and moon selection is going to be continuing. So before I stop, this picture was above the bed in the rather cheap hotel that I was in Hochbruch, and it struck me immediately that, oh, yeah, there's some very mock maths in this picture, and I sort of, yeah, discounted it. And then I noticed a little bit later, oh yes, the Alliance Arena is in this. Oh yeah, so that is the nearest local feature that highlighted that most tourists would notice. But then I noticed in the background, oh yeah, there's the Milky Way and there's stars in here. Okay, so they're acknowledging some of the backgrounds to Garching in astronomy. And then you also notice that the supernova center is this rather gray background. But the thing that really popped out at me after a while is that these rather abstract circles that look like engineering drawings that I did when I was at school of bits of mechanics in a steam engine. If you notice, it has this rather odd sort of triple bridge and a rather odd looking shape here and circles, and we're about here. This is the ESO, a plain view of the ESO headquarters. So for some reason, someone seems to think that everyone staying in Garching can't escape ESO, although very few of the people staying in these rooms might actually recognize their location in this rather abstract and really quite disturbing map. A good job it was dark in my room. I didn't have to look at this the whole time. But if you are staying in the B&B hotel, this will be in every room as far as I can work out. So thank you.